Before Earth existed, a cosmic storm shaped everything we know today. Our solar system began as a massive rotating cloud of gas. Gravity slowly pulled particles together, forming dense and hot regions. These early clumps eventually became the Sun at center. Around the newborn Sun, a spinning disk of material formed. Dust and ice particles collided repeatedly within the protoplanetary disk. Small grains gradually stuck together, creating larger rocky bodies. These growing bodies are known as planetesimals in astronomy. Collisions among planetesimals formed even bigger protoplanets over time. Temperature differences shaped inner rocky and outer gas giants. Near the Sun, only metal and rock could survive heat. Farther away, gases and ices formed massive planetary cores. Mercury formed first as small, dense metallic world closest Sun. Venus developed thick atmosphere, trapping intense heat from Sun. Earth formed inhabitable zone, allowing liquid water oceans. Mars became a smaller, colder world with dusty red surface. Beyond Mars, asteroid belt remnants never formed a full planet. Jupiter grew massive, capturing huge amounts of hydrogen gas. Its strong gravity shaped many objects in early solar system. Saturn formed with iconic rings made of ice and dust. Uranus tilted sideways due to massive ancient cosmic collision. Neptune formed farthest with strong winds and deep blue color. Solar wind cleared leftover gas from early planetary system. This process took millions of years to complete fully. Early solar system was chaotic with constant violent collisions. Comets formed in distant icy regions beyond Neptune orbit. These icy bodies still travel through solar system today. Asteroids preserve ancient materials left from early solar system formation. Planets continued growing by absorbing smaller nearby space objects. Eventually, orbits stabilized, forming the structured system we see. The Sun contains more than 99% system mass. Nuclear fusion inside Sun powers heat and light energy. Planets orbit Sun due to its powerful gravitational pull. Each planet follows an elliptical path around the Sun. Early magnetic fields influenced planetary atmosphere formation and evolution processes. Solar radiation shaped surfaces of inner rocky planets significantly. Outer planets developed thick atmospheres composed mainly of gas. Moons formed alongside planets or were captured later gravitationally. Earth's unique conditions allowed life to eventually emerge here. Water delivery from comets likely helped form Earth's oceans. Geological activity on Earth recycled materials, shaping its surface. Plate tectonics slowly reshaped continents over billions of years. Solar system continues evolving even after billions of years. Asteroids occasionally collide with planets, altering surface features significantly. Scientists study meteorites to understand early solar system history. Space missions continue revealing secrets about planetary formation processes. New discoveries refine our understanding of cosmic evolution greatly. The solar system remains a dynamic and fascinating structure. Its formation story helps explain Earth's place in universe. Every planet holds clues about ancient cosmic origins revealed. Gravity remains the fundamental force shaping planetary architecture today. Early solar nebula conditions determined final planet composition details. Heat and pressure transformed early planetary materials over time. Solar system formation theories continue to evolve scientifically today. Telescopes help astronomers observe distant forming star systems clearly. These observations mirror our own solar system's early history. Each planet's unique features result from formation conditions experienced. Solar system stability allows life to exist on Earth. Without precise cosmic balance, planets could not sustain orbits. This delicate system continues functioning after billions of years. Understanding solar system formation reveals our cosmic identity deeply. The Sun's birth marked beginning of planetary evolution process. Planets still carry evidence of their violent origins today. Solar system remains subject of ongoing scientific exploration today. Our cosmic neighborhood tells story of creation and transformation. The early solar system remained unstable for millions of turbulent years. Countless collisions shaped planets into their current final forms gradually. Gravity continued pulling leftover debris into growing planetary structures. Some planetesimals shattered completely during violent space impacts. Others merged to form increasingly larger celestial bodies. Heat from impacts melted early planetary surfaces repeatedly. This melting allowed heavier elements to sink into cores. Lighter materials rose, forming early primitive crusts on planets. The Sun's energy gradually stabilized surrounding orbital environment. Strong solar radiation influenced atmospheric development on inner planets. Mercury lost most atmosphere due to weak gravitational pull. Venus developed runaway greenhouse effect, trapping extreme heat efficiently. Earth maintained balanced temperature, allowing oceans to form. Mars cooled faster, becoming dry and geologically inactive later. Asteroid belt remained scattered debris, preventing planetary formation fully. Jupiter's massive gravity cleared nearby orbital paths effectively. This protected inner planets from excessive asteroid bombardment. Saturn's rings likely formed from shattered icy moon's fragments. Uranus and Neptune migrated outward during early system reshuffling. Planetary migration reshaped entire architecture of solar system structure. Early Sun was slightly dimmer, but highly active magnetically. Solar flares frequently bombarded young planets with radiation bursts. Magnetic fields help protect developing atmospheres on some planets. Earth's magnetic field became crucial for long-term habitability. Water vapor condensed, forming early oceans on young Earth. Comet impacts delivered additional water and organic compounds. These materials may have contributed to life-building blocks. Early Earth experienced constant volcanic activity, shaping surface terrain. Continents slowly formed through repeated cooling and crust movement. Atmosphere evolved gradually, from toxic gases to stable mixture. Oxygen began accumulating due to early microscopic life activity. This transformation changed Earth's atmosphere forever over time. Other planets lacked similar biological processes preventing oxygen buildup. Solar system continued clearing dust through solar wind pressure. Remaining gas clouds dissipated, leaving stable planetary orbits. Moon likely formed after massive collision with proto-Earth. Debris from impact eventually coalesced into Earth's natural satellite. The Moon stabilized Earth's axial tilt over millions of years. This stability allowed seasonal cycles to develop consistently. Without Moon, Earth's climate would be far less stable. Inner planets remained rocky due to intense solar heat. Outer planets captured vast hydrogen and helium gas envelopes. These gas giants grew far larger than terrestrial planets. Jupiter became dominant gravitational force in entire system. Its presence influenced asteroid distribution significantly over time. Saturn developed complex ring system visible even from Earth. Ice particles in rings constantly collide and reform structures. Uranus rotates almost sideways due to ancient collision event. Neptune exhibits fastest winds in entire solar system. Distant Kuiper belt formed beyond Neptune orbit region. Kuiper belt contains icy remnants of early solar system. Pluto resides in this region as dwarf planet. Many comets originate from distant Oort cloud reservoir. These comets occasionally enter inner solar system paths. Their tails form when heated by Sun's radiation. Meteor showers occur when Earth passes comet debris trails. These events provide clues about solar system composition. Ancient impacts shaped cratered surfaces on many planets. Mercury and Moon show heavy cratering from early bombardment. Earth also experienced similar impacts, but erosion erased many. Geological processes continuously reshape planetary surfaces over time. Tectonic movement recycles Earth's crust repeatedly through history. Other planets lack active plate tectonic systems currently. Mars shows evidence of ancient river and lake systems. These findings suggest past conditions may have supported water. The solar system continued evolving long after initial formation ended. Planetary orbits gradually became more stable through gravitational balancing. Small disturbances still occur due to asteroid and comet interactions. Early chaotic collisions slowly decreased over millions of years. The Sun entered a long, stable phase of hydrogen fusion. This stability allowed planets to develop long-term geological processes. Earth's atmosphere continued changing through volcanic and biological activity. Carbon dioxide levels fluctuated, shaping early climate conditions. Oceans played a major role in regulating planetary temperature balance. Continental plates drifted, forming early supercontinent structures. These supercontinents repeatedly broke apart and reformed over time. Life began to diversify in Earth's stable aquatic environments. Other planets did not develop similar biological complexity. Mars likely lost most of its atmosphere due to solar wind. Venus underwent extreme heating, making surface uninhabitable today. Outer planets remained cold gas-dominated worlds without solid surfaces. Jupiter's Great Red Spot formed as massive, long-lasting storm. Saturn's hexagon-shaped storm puzzled scientists for decades. Uranus and Neptune retained deep atmospheric layers of methane gas. Their blue colors result from light absorption by methane. Solar system's gravitational balance prevents planets from drifting away. Each planet follows precise orbital resonance patterns around Sun. These resonances help maintain long-term orbital stability. Asteroid belt remains a region of constant minor collisions. Some asteroids occasionally get redirected toward inner planets. These impacts have influenced Earth's biological history significantly. Mass extinction events may have been triggered by asteroid impacts. Such events reshaped evolution of life on Earth repeatedly. Lunar craters preserve record of early solar system bombardment. These craters provide timeline of ancient cosmic events. Scientists use radiometric dating to study planetary formation ages. Meteorites offer valuable clues about early solar system materials. Some meteorites contain organic molecules from space chemistry. These findings suggest complex chemistry existed before life. The Sun continues slowly increasing brightness over time. This gradual change affects long-term planetary climates. Earth will eventually become less habitable in distant future. Solar evolution will ultimately transform entire system structure. Outer planets may shift positions slightly over billions of years. Kuiper belt objects continue orbiting in distant icy region. Oort cloud remains hypothetical but widely accepted by scientists. It likely contains trillions of icy cometary bodies. These objects are weakly bound to solar gravitational influence. Passing stars can disturb Oort cloud orbits occasionally. Such disturbances send comets toward inner solar system. These comets may create spectacular sky events on Earth. Ancient humans may have observed similar celestial phenomena. Solar system history is recorded in planetary geology layers. Each layer reveals past environmental conditions of planets. Earth's sedimentary rocks preserve ancient climate information. Volcanoes played a key role in shaping early atmospheres. They released gases that formed secondary planetary atmospheres. Over time, these atmospheres became more chemically stable. Oxygen production drastically changed Earth's atmospheric composition. This shift enabled evolution of complex multicellular life. Other planets lacked stable biological feedback systems. Solar radiation continues influencing planetary surface chemistry today. Space weather affects magnetic fields of planets constantly. Earth's magnetosphere protects life from harmful solar particles. Without it, surface radiation levels would be extremely high. The solar system remains active despite its ancient origins. Small-scale changes continue shaping planetary environments slowly. Gravity ensures long-term cohesion of entire system. Every planet carries history of cosmic formation within itself. This ongoing evolution connects present universe with its past. The solar system structure hides many ancient cosmic secrets. Each planet preserves clues about early formation conditions within itself. Scientists study planetary cores to understand original material composition. Earth's layered structure reveals billions of years of geological change. Inner core formation released heat that shaped early Earth evolution. This internal heat drives volcanic and tectonic activity today. Mars shows signs of once active volcanic and watery past. Huge volcanoes, like Olympus Mons, formed during ancient eruptions. Evidence suggests Mars once had flowing rivers and lakes. These features indicate a warmer and wetter ancient climate. Venus likely had oceans before extreme greenhouse effect developed. Runaway heating transformed Venus into hostile surface environment. Thick clouds now trap heat, making surface extremely hot. Mercury's surface remains heavily cratered and geologically inactive. Its closeness to Sun stripped away most atmospheric gases. Solar radiation constantly bombards Mercury's exposed rocky surface. Outer planets remained largely unchanged due to distance from Sun. Jupiter acts as protective shield for inner solar system planets. Its gravity deflects many comets and asteroids away. This shielding role may have helped Earth sustain life. Saturn's ring system continues evolving through constant particle collisions. Some rings may be relatively young in astronomical terms. Uranus and Neptune show strong seasonal atmospheric variations. Their extreme distances create very long orbital years. Neptune takes over 160 Earth years to complete one orbit. Kuiper Belt objects orbit in icy darkness beyond Neptune. Some of these objects occasionally become short-period comets. Pluto shares region with many similar dwarf icy bodies. These distant worlds preserve untouched material from early system. Their study helps scientists understand planetary building blocks. The solar system formed from collapsing molecular cloud fragments. This collapse triggered rapid heating and rotational acceleration. Conservation of angular momentum created spinning disk structure. Central mass concentration eventually ignited nuclear fusion in Sun. Surrounding disk material slowly cooled and condensed into solids. Dust grains repeatedly collided, forming larger rocky aggregates. These aggregates eventually became protoplanets through gravitational attraction. Each protoplanet competed for material in surrounding orbital zones. This competition shaped final planet sizes and compositions. Some regions remained too unstable for full planet formation. Asteroid belt is leftover material from failed planetary formation. Jupiter's gravity prevented asteroid belt from forming a planet. Early solar system had frequent high-energy collisions. These impacts reshaped planetary surfaces multiple times. Earth experienced intense bombardment during early formation period. This phase is known as late heavy bombardment era. Many lunar craters date back to this ancient period. Life on Earth emerged after this violent phase ended. Stable conditions allowed chemistry to develop more complexity. Organic molecules formed in oceans under early atmospheric conditions. Lightning and volcanic activity contributed to chemical reactions. These processes may have helped form early life precursors. Solar radiation provided additional energy for chemical synthesis. Earth became chemically dynamic system, supporting increasing complexity. Oceans acted as natural laboratories for early biochemical evolution. Other planets lacked stable liquid water environments. This made Earth uniquely suitable for life development. Plate tectonics recycled nutrients essential for biological systems. Carbon cycle stabilized long-term climate conditions on Earth. This balance maintained habitable conditions for billions of years. Solar system continues moving through Milky Way galaxy. It takes about 230 million years to complete one orbit. Galactic environment may influence comet activity occasionally. Nearby stars can gravitationally disturb distant Oort cloud objects. These interactions connect solar system to broader galaxy dynamics. The solar system continues evolving even in its modern stable state. Subtle gravitational interactions still shape planetary orbits over time. Scientists predict slow orbital changes across billions of future years. The Sun will eventually exhaust its hydrogen fuel supply. This transformation will dramatically alter entire solar system structure. Before that stage, the Sun will gradually grow brighter. Increasing solar output will slowly affect Earth's long-term climate. Oceans may eventually evaporate under intense solar heating conditions. Inner planets will become increasingly uninhabitable over vast timescales. Earth's biosphere depends entirely on Sun's stable energy output. Jupiter and Saturn will remain gas giants throughout solar evolution. Their massive atmospheres will continue influencing surrounding space environment. Uranus and Neptune will keep orbiting in distant cold regions. Kuiper belt objects will persist as icy remnants of formation. Occasional cometary intrusions will still occur in inner system. These rare visitors provide ongoing insight into early solar history. Solar system structure reflects balance between gravity and motion. This balance has persisted for over 4.5 billion years. The Sun formed first and shaped everything around it. Without Sun, no planetary system could have developed at all. Gravity pulled matter together from chaotic cosmic dust cloud. Rotation of collapsing cloud created flattened disk structure. Temperature gradients determined composition of forming planets. Inner region produced rocky terrestrial planets like Earth. Outer region formed massive gas and ice giants. Each planet carries unique record of formation history. Studying these worlds reveals secrets of cosmic origins. Meteorites act as time capsules from early solar system. They preserve chemical signatures from ancient space materials. Scientists analyze them to reconstruct planetary formation timeline. Space missions have visited many planets for direct observation. These missions revolutionized understanding of planetary environments. Robotic probes continue exploring distant regions of solar system. New technologies allow deeper study of planetary atmospheres. Telescopes detect forming planetary systems around other stars. These discoveries show solar system is not unique. Many star systems follow similar formation processes. This confirms universal nature of gravitational physics. Planet formation is common across the universe. Each system develops based on local conditions and materials. Earth remains only known planet supporting complex life. This makes its formation history especially important scientifically. Conditions required for life are extremely specific and rare. Stable orbit within habitable zone is essential factor. Presence of liquid water is another critical requirement. Protective magnetic field helps maintain surface habitability. Geological recycling supports long-term environmental stability. All these factors aligned perfectly on early Earth. This alignment resulted from billions of years of cosmic evolution. Solar system formation created conditions necessary for existence itself. The story of planets begins in collapsing interstellar cloud, ends with structured system orbiting stable central star. Yet this system remains dynamic and ever-changing. Small cosmic events continue shaping planetary futures slowly. Solar system holds clues to universal processes of creation. Every orbit reflects ancient balance of cosmic forces. Every planet is product of violent and creative history. Understanding this system reveals our place in universe. It connects human existence to vast cosmic timeline. We are part of ongoing story written in stars. Solar system formation demonstrates power of gravity and time. These forces transform chaos into structured planetary systems. From dust clouds emerged worlds and possibilities for life. This transformation continues shaping universe on grand scale. Our solar system stands as evidence of cosmic evolution.